Hello, today we're going to be talking about Lives of Stars. This is an introductory section to it. You can go in a lot more depth if you actually go do a little Google search, but this will hopefully whet your appetite. What I'm going to talk about today is the actual start of a star through a nebula and actually getting to a point called a protostar, but you can go a lot smaller than that. But then we're going to talk about the star as it grows, it reaches equilibrium, then goes through its death throes. This is a very nicely done diagram to actually show you the star's life cycle versus maybe a human life cycle, and we'll talk about that thing in a few seconds. But anyway, the first thing I want to talk about is that before we actually get to the protostar stage, we have to start with a nebula. And a nebula, as I've said before, is a big cloud of dust and gas, probably hundreds or thousands of light years across, very low density for the most part, but gravity starts to pull this stuff in, and as gravity starts to pull it in, material ends up being pushed in toward the inside, and it gets more and more dense. As it gets more and more dense and there's more and more friction, we actually end up with friction, and the friction actually starts this thing to start glowing. So right here we have what's called a protostar. Protostar is a star that actually has not reached the point where it becomes a star, hasn't reached nuclear fusion. In this picture also, which I'll show my kids when we get closer to the solar system, which is the next section, we get what are called planetesimals. And these planetesimals, you can see, actually go through a process of coalescing. They become larger by running into each other, and as they get bigger and bigger, these planetesimals become planets, and we'll talk about the inside planets becoming the terrestrial planets and the outside becoming the Jovians, and that's all dependent on temperature. But this is the protostar stage. Then we move over here, and what we get here is we get a star is born. And in order to actually get a star, we need the internal temperatures to increase hotter and hotter and hotter to reach a magic temperature of 10 to the 6th K, 10 million degrees K, and if we do that, we get what's called nuclear fusion, or what they're saying right here is fusion ignition, and with that we get hydrogen ions moving fast enough together that they actually come together and make helium. Whoops, sorry. And if we get helium, we actually get the production of tremendous amounts of heat, and this is actually what powers stars. Our sun, which I've talked about before, has an internal temperature of about 15 million degrees K, or 15 million K, so we have ample heat to actually get this. We have redder stars, we have hotter stars, redder meaning cooler, hotter blue and white stars, but we actually get those, and we get the stars born. Once the star is born, if you take a look at this, we actually have gravity, which is the blue arrows, trying to push these in, and we have heat expansion by the red arrows trying to push them out. And I'm not really talking about this diagram as the way the diagram was set up to be. I'm using this diagram to give the idea of what is called, and I'm going to draw it here, it has nothing to do with this. If I call this one number 1, this is number 2, this is going to be our number 3, and this is our number 4 diagram. What I'm going to write here, and I'll erase it, actually deals with number 3, and this is what's called stellar equilibrium. And stellar equilibrium says when this thing produces enough heat to counteract the gravity which is trying to pull it in, it reaches a steady state, stellar equilibrium. And it will do this with two things. It has gravity, which is actually trying to make this star shrink, and we have heat of expansion, which is trying to make this star increase in size. What's going to give out first is the fusion. Sooner or later this star will run out of hydrogen. There are no gas stations up there to produce more hydrogen for these stars, so it is a finite amount. And when the star actually starts running out of hydrogen, at some point heat is going to dissipate and gravity will pull this star in, and at that point we enter number 4, and at that point we take helium and we actually push them together, fuse them, creating much higher internal temperatures. I'm not exactly sure how high, but tens of thousands of millions of degrees, tens of millions of degrees, sorry. And what will happen is now the heat, and actually what we'll get out of this, our sun is capable of producing carbon and probably iron. Doesn't really give the rest of the minerals, the elements that are actually in the earth, or what is experienced or explored or seen out in the universe. So we need the much larger star to actually make the things that created the earth. Our sun is probably not a first generation star, it's probably second or third. We had much larger stars creating the things that are here on earth. But this star will actually fuse helium into making larger elements, create a lot more heat, and at that point it will start to expand. And with that expansion, it's going to outdo the amount of gravity that can pull it in, and what's going to happen is the star will continue to expand, and depending on how much mass it has, it may expand into something called a supernova, or it may just move into something called a red giant. But anyway we look at it, we're going to have a last bad day here on Earth, and from there on out things will change. Okay, so we have what are called main sequence stars. These are very similar to what you would consider young adulthood. Then we get red giant stars, supergiant stars, hypergiant stars, and what's called middle age. And then we get the white dwarfs and or the black hole, depending on how massive this nebula was that came together, and how big the explosion is over here in number 4. They equate it to like fetus for the protostar, infancy for nuclear fusion. You can see these are getting taller and taller, main sequence, and like I said, red giant, hypergiant, white dwarf, black hole. Okay, and then the next thing I did is I actually talked about what's called an HR diagram. HR diagrams are actually named after 2 astronomers, Hertzsprung, a German, and Russell being a American. And what they did is they actually looked at every star as being the same. What kind of characteristics can I actually get to a star? They said all stars have heat. They all have temperature. Now this is the temperature of the surface of the star. And if you remember from the sun's temperature is right around 6,000 K. So we're going to be on this line somewhere, somewhere from about 6,000 down to like G2. Luminosity, these things are in sun lumens. Talking about how bright the sun is, comparing it to all stars. I do have to sort of come over here and tell you absolute magnitude. Absolute magnitude is actually looking at a star from a certain distance, and what it's like is going through and actually getting a star from at a distance of 26 light years. And that means that for the sun, we're going to have to go a lot farther away, and for a star like Betelgeuse, we're going to have to get a lot closer. In fact, most stars will have to get a lot closer. So most stars will actually get bigger and brighter in that sky, and a few, like the sun, would actually get a lot dimmer and a lot smaller. Okay, so sun lumens, looking at the sun from 26 light years away, we say we have 1 lumen. So that number right there works out to a +5, and if you notice the numbers as they get smaller and into the negative values, they actually get brighter because this is the bright end. And this is the dim end. Same thing, we get bright over here and dim over here. This is the cool end. This is the hot end. And the same thing, we get hot on this side. You can see maybe 50,000 K. This is the cold side, maybe down into like 2,000, 1,000. They can get cold enough that they can no longer be seen visibly. Spectral class actually sort of deals with color. I'll show that to you in the diagram that's a little lower. You can see it down here. And basically we've got the red, orange, yellow. The yellow gets lighter, turns more bluish, and gets really dark blue. White's in there also. But that's the spectral class. Spectral class, not sure how this ever came about, how these numbers actually were utilized, but this is the O range. This is the blue hot, really hot range. Each one has a subdivision from 0 to 9. An O0 or an O2 or an O5 or an O7 are all classifications. The larger the number gets, the less colorful or cooler the star actually gets. So an O3 would be hotter and brighter probably than an O8. Another characteristic we'll have to talk about is size. And then the B's, same things. A's. How are you going to remember these? There's a mnemonic, and the mnemonic is O, B, A, fine, girl, kiss me. Sort of a stupid mnemonic, but if you remember that mnemonic, you can remember the placement of O, B, A, F, G, K, and M. Okay, the first thing they did is they actually said that all stars have the same temperature, they all have a brightness, and we can actually plot every star based on that. And the first one we're going to plot is actually the sun, and right around this 6,000 and right around this 1, someplace right around here, I'm going to say there's the sun. Now I'm going to draw the sun as a yellow star. I'm drawing these rays out sort of like the corona. I'm going to draw that one there. The rest of the stars I'm going to pick just one color, and I'm going to pick a color that doesn't show up very well on there, black. And what they also did is they found a star that would be like in this place. And they found a star that was down here. And they found a star that was up there. And they found a star that was down here. And now we can start looking and comparing these two stars. If I call this one star number 1, we call this one star number 2, we call this one star number 3, and we call this one star number 4. What does star number 1 and 2, what do they have in common? Well, if you take a look, they are about the same spectral class and about the same temperature. Okay, well, how are they different? One's down here at like plus 12, the other one's over here at like minus 7. One of them tends to be a lot brighter than the other. That's this one. Okay, how are 2 and 3 alike? Well, they have about the same luminosity and the same absolute magnitude, but they differ in terms of temperature. How can I make a hot star have a brightness and make a cool star that actually has the same brightness? We'll talk about that in a little while. What about 3 and 4? Have the same temperature, same spectral class. One's a lot dimmer than the other. And then what about 1 and 4? They have the same absolute magnitude and luminosity, but what they don't have is the same temperature or spectral class. So you can start comparing stars using these characteristics. And what they did is they just started plotting stars. And I'm just going to kind of plot stars, not having to do anything with their size. I'm going to plot some stars, and they found stars there, and they found a couple stars over here, and they found some stars over here, and then they found some more stars over here. And again, the circles that I'm drawing have nothing to do with color, size, brightness, or anything. They're just positions. And they found another one there, and they found another one there, and they found one there, and they found one there, and they found another couple in there. And I hope you guys can actually see that what they found was that there was a pattern to these stars. There seems to be a lot of stars in this one area, which I'm going to circle with this blue or turquoise. And they seem to find some stars in this area, and they seem to find some stars in this area. Now there are rogue stars. These are stars that are maybe a little confused on what area they're supposed to be in. But what they started to do is they started to describe these stars. Well, what do these stars look like? They're relatively cool. They're an M class, which is a red star. But so are these. This is the red end. So any star sort of in this area is going to be red. They get more orange as they move over to K's and G's. They get more yellow as they go from G's to F's. And they get more white as they go from F to A. And they get more blue as they go from A to O. But these are red stars. These are red stars. How come these are a lot brighter than those? Only way you can make a star brighter that has the same temperature is you have to make them big. These are the red giants. And they can actually be supergiants, and they can even be what's called hypergiants. And we'll see those in a YouTube video I'm going to show you in a minute or two. Actually, a few. The red stars, and then we have orange stars, we have yellow stars. These guys are all going to be in the blue area. Not writing it in blue. Probably should write it in blue. This is the blue side, or white side. This is the red orangish side. We have some stars that are up here that are blue. You have some other stars down here that have the same temperature. How do you make these bigger? Well, these guys are called blue giants. Okay, how do you make these blue stars small? Well, first we'll actually write it as white. These are I need to make it a little more white. Not white, it's really gray. These are the white dwarfs. How do you make a star that should actually be pretty hot, not very bright? You make it small. Okay, so these are the three subcategories of the HR diagram, and no matter we look at the stars in our galaxy, the Milky Way, or we look at stars in other galaxies, they all seem to fit in these three categories. What does it mean? Well, we got stellar equilibrium. Oh, we didn't tell you what this one was. This is the main sequence stars. And these are actually stars that are like the sun, even though some of them are much dimmer and cooler, and some of them are greatly hotter and larger. If you take a look, you can see very easily that we are not an average star. An average star would put it like in that area right there. We're less than average in terms of brightness. We're less than average in terms of temperature. But it is still a very special star because it's ours. Okay, let me show you these two things. It's not this one first, it's this one first. This is talking about stellar illumination, and you can actually see this is coming from Astro, UNL, EDU, Class Action, Animations. And if you go to there, you can see lots of cool things. But this is showing a spectral class, and you can see as I change from an A, if I change from an A to an O, I get more blue. As I go back through A's, I get a white star. As I go through F's and into G's, I get yellow stars, and then I get orange, and then I can get red. And I can actually increase it, because right now what we're at a, I don't know what I'm clicking to get that thing to open up, but we're at a 1. You can see, so this is the sun's size, but I can actually change the sun's temperature, and you can see that the luminosity changes immensely. That star right there is 7.18 times 10 to the third lumens, and that star right there is 1 because we are a G2 star. I can make the star smaller, and you can see the brightness changes as I increase and decrease size. I can make the star bigger, all the way to 100 times larger, and again change the color. I can also go to this site. This site is actually talking about, probably should have gotten a star that's like. This is the main sequence, so what I can do is I can actually bring that star down to about 6,000 degrees, which is right there. Bring it down just a tad and get it to 1 lumen. A little cooler. Stop it. Stop it. 6,000, 1 lumen. There is. Okay, this is not fun. 6,000, 1 lumen. There is our sun. This is the HR diagram. I can move this thing up the red line, and you can see the star changes in reference to the sun. They get really big. In fact, I can make them so big that the line actually looks like it's vertical. And then moving over here through the white, moving into yellow, orange, and then finally red stars, and then bring it back down to smaller stars, and I can slide it right up the HR diagram. These are the main sequence stars. If you want to see where the other groups are, I can slip through the different white dwarfs, and you can see that the luminosity and temperature does change, even though they're going to stay very dim. We're talking about a number even all the way up there that's just 2/100ths of the brightness of the sun. I can go to the red dwarfs, the yellows, all the way back up there, move into the blue giants, white giants, and then move into the red giants. And you know, the red giants can be kind of small, and they can also be very, very large. Okay, so here's sort of the same picture. This is all set up, and these are the two sites I just showed you. Have lumens. Our sun would be 6,000. Our sun would be like right about that star, somewhere right in that area. And you can see we are colder, and we are not as bright as what an average star would be, which would be in the middle. But this one actually shows you color and size, which I think can be very useful in understanding the HR diagram. Okay, in terms of the life of the star, we have three basic choices. We have number 1, we have number 2, and we have number 3. And if we talk about number 1 for a second, these are going to be stars like the sun, sun-like stars. They're going to have 0.8 to 11 times the mass of the sun, so they can get actually fairly large. But you can see this is going up to 50, and this is more than 50. Starts out as a sun. Now, they're actually not talking about the nebula and the protostar. They're saying the sun is there. It's going to burn through its hydrogen into helium, generating heat and light, and our sun is supposed to do that for almost 10 billion years. But it will run out. It'll actually shrink and then get really hot, fusing helium, and then it'll actually start enlarging. It may actually get to the point where our original sun was like right there, and we have Mercury's orbit, and we have Venus's orbit, and we may even have Earth's orbit inside this thing, this red giant. So it's going to get pretty good size. And what it'll probably produce is a planetary nebula. In the very center will be the exposed core of this thing, which is going to be the white dwarf, and the white dwarf will actually go here and get cooled off, and it'll end up being black. It'll blotch itself out of the HR diagram because it will not be producing enough light for heat. If we make them even bigger than that, we have a huge star. You can see there are definitely huge stars compared to our sun. And this one will actually do the same thing. It turns out that it actually burns its hydrogen much faster than ours, so it's going to run out of its life much, much, much faster. And when it comes together, it's going to have a lot more mass. It'll start fusing a lot more heavy elements. You may get iron, gold, magnesium, manganese, even other things. And then this one will go through its explosion. We call those supernova, and what's left after a supernova of a solar mass of 11 to 50 is what's called a neutron star. Neutron stars, very dense. A teaspoon would weigh millions of tons. Very dense neutron star. These things actually spin very fast. We can call them pulsars. And it probably has that in here somewhere, but these do spin. They say they're small and dense, about 10 miles in diameter, 1.4 times the mass of the sun, incredibly dense material. And then if we have even bigger stars, ones that are greater than 50 solar masses, giant stars. So we went from a star like the sun to huge stars to giants. This supernova, this red giant is going to be even bigger. This supernova is going to be even bigger, and this will actually leave something that's called a black hole, a singularity, something that is dense enough that not even visible light can escape. These are all coming from zoonschool.com. You can look those up and actually learn more. They do have text along with these pictures, but three really good pictures. Size of the stars. These are pictures where we actually have Mercury, and then we have we have the moon, we have I should probably read what I have here. This is Mercury and Mars and Venus and Earth, and then we shrink Earth down to this size, and then we can actually put Neptune and Uranus in there, and then we can see Saturn and Jupiter, our biggest planet, and then if we shrink Jupiter down to this size, we can actually put Wolf 359 up there, and then we can finally put the Sun, and then we start comparing the Sun to other stars. And you can see the Sun not even showing up on this picture, and it gets bigger and bigger and bigger. Take the biggest one out of here, which is Aldebaran and Taurus, and put it down to here, and we can get Rigel, we can get Antares, we can get Betelgeuse. These stars have just about the same brightness, but this one is twice as close, 520 light years. This is about 900 light years. If you take a look at those differences, it shows you how much brighter this little blue star is. Put it twice as far away, and it almost has the same brightness as this big star, twice as close. Then if you take that big star and put it there, we have a star in Cepheus, another star in Cepheus, so Mu, which makes the M letter in the Greek alphabet. So there are a lot of stars in Cepheus that are brighter than this, and I'll show a video that will actually show this. And then we have VV, which is even a dimmer star in the constellation Cepheus A, and then we go to VY, which is even dimmer in this constellation, Canis Major, than this was in Cepheus, and this is the largest star known to man. And I'll go show you that video now. So, here we go. I'll let the music speak for itself, although I will be talking through this video. So we throw Pluto, which is now a dwarf planet, but we throw that in. That's the smallest of our planets. We go out to the Moon, gives you the size of Pluto. Remember, the Moon's 1/6 the size of the Earth. We go out to Mercury, maybe even looks more like the Moon than the Moon. Then we make it to Mars, snow-capped, does have ice, although it's probably dry ice. Then we go to Venus, our twin, because it's about the same size, although when we get into the solar system we'll find out that it's about as opposite as the Earth as you can get. Then we have the Earth, beautiful blue marble. Out to Neptune, probably the prettiest planet, I think. Then we make it out to Uranus, it does have rings, Neptune has rings too. You can see it spinning almost sideways. Then out to Saturn, the great ring planet. And then into Jupiter, beautiful red spot, 3 times the size of the Earth. And then we finally make it out to stars. There's the Sun. And the Earth is right there. Oh, Earth is gone. Here's the brightest star in our sky. It's actually Cygnus, Canis Major. There's Pollux in Gemini. 2 brightest stars. Then we make it out to Arcturus and Bootes, the herdsman, which is the alpha star in there. And Aldebaran, the eye that's actually looking at Orion, and Taurus the bull, the orange giant. Then we make it to Rigel, second brightest, the beta star inside of Orion. And Eta Carinae, which is in the Carina southern constellation. Pistol star, which is a blue giant, not in our eyesight visible spectrum at all. Rio Cassiopeia, Cassiopeia, not one of the W stars, but you can see it in there. Antares, alpha star in Scorpius. Betelgeuse, alpha star in Orion. Mu Cephei, not in the house of Cepheus, but down there. Not sure whether or not you can see it. You probably can with binoculars. And then VV Cephei inside the house, right, the hypergiant. And then all the way to VY Canis Majoris. Outside of Canis Majors, there's Sirius, the largest known star. And then they zoom in, give you some idea. Sooner or later you'll see the Sun again. And there's the Sun. And then zoom in some more, you can even make out the size of the Earth. So that is a massively huge star. Okay, thank you for that. If I go back, there is one I'm going to show my kids in class next week, which is this one. I'm going to try to enlarge this. I know it's going to be larger than the screen, but I think you'll get the drift. Have bigger objects floating in the universe? You'll find out they're really big. Okay, so this one's starting with the moon, going to Mercury, going out to Mars, Venus, Earth, if you didn't know, you are there, Neptune, Saturn without its rings, that's the show Uranus, Jupiter, planets over on the left, here come stars. We could actually show smaller stars, but you get the idea. There's Sirius, Pollux, Arcturus, Aldebaran, Rigel, Pistol Star, one we can't see with our eyes, Antares, my constellation Scorpius, Lucifer, Red Supergiant, VY Canis Major, Hypergiant, and this one's going to zoom in and you can see the Earth way over here. Pretty hard to actually see the two together. I'm going to tell you about the diameter. That's 2.8 billion kilometers. You go in a passenger jet traveling at 600 miles an hour or 900 kilometers per hour, you can make it around this star in 1,100 years. Pretty darned amazing. And then we talked about Nebula, even bigger than that, and galaxies even bigger than that. Okay, we're going to let that one slide. We're going to go back into here. This is our Milky Way galaxy. Here's the position of the sun. We can look in these directions. We have 0, which is we consider like the north, all the way up to 360 going this way. This would be 180. If you actually look to some of these really light areas, like looking sort of in this direction or even this direction, we look into a point in the sky where we don't really see anything. This is what's called Hubble's ultra deep view. We trained Hubble to where we were not able to see a thing with another type of a telescope, and we pointed this, and almost everything you see in this picture is a galaxy. So there are literally hundreds of billions of galaxies out there, all of them holding maybe hundreds of billions of stars. There are a bunch of stars out there, all going through their life cycle, all being born, all living, all dying, all creating new nebula, being created by older nebula, just going back and forth and back and forth and back and forth. Okay, appreciate it. This was the life of the stars. I'm looking primarily at the HR diagram. Thanks for stopping by. Bye-bye.